So today we're going to talk about container overlays and specifically hiding large number of files in container overlays on clusters. In the Alliance, so formerly called Compute Canada, many clusters use a distributed, well, actually all clusters use distributed file systems. So in fact, if you click on the link right here, open in Firefox, if you click on the link right here, there's a table here that lists the type of file systems and the quotas, etc. For each cluster. So for example, in CEDA, you see that in CEDA home, right here is based on a Lustre file system. The same for Scratch, the same for Project. If you go to Gram, for example, you see that on Gram, both Scratch and Project are Lustre based. So Lustre is a distributed file system that is optimized for HPC. It's very different from your typical hard drive or solid state drive on your computer because it actually comprises hundreds, more likely thousands of drives. And the files are stored in blocks, well, as objects on those drives, but very often a file doesn't really have a specific location in the sense that it could be striped across multiple drives, divided across multiple drives, it could be cached, etc. So these system is supposed to be very scalable, can scale up to hundreds of servers, so both metadata and object storage servers that control access to the files, to tens of petabytes of storage and over a terabyte per second of aggregate throughput. So on a cluster, typically when you have this parallel file system, there are multiple clients that connect to this distributed file system through the network. So clients typically are individual cluster nodes, and as you know, on a big cluster, there are hundreds and hundreds of cluster nodes, and all these clients see the same file system, essentially a unified namespace for all the files and directories stored on this file system. Of course, when you try to write into this file system, it gets a little bit complicated because the file system, so Lustre has to keep track of which file is being written to and prevent, simultaneous writes into the same file. So this adds, some levels of complexity to this, and there are multiple levels of cache, also data replication at different levels to improve I/O speeds and to keep data highly available. So to summarize, Lustre has been, and other distributed file systems as well, have really been designed to provide a very high bandwidth and very high I/O speed for writing of large files, so basically large continuous blocks of data. And on the flip side, they're quite bad. So Lustre is quite bad when it comes to storing a large number of small files, right? So having a large number of small files on the Lustre file system actually puts quite a bit of stress on the metadata service and strains the system not just for yourself, but for everybody else trying to do work on Lustre, right? So for this reason, we have all these quotas implemented on the file systems, both for the number of files and, primarily for the number of files. So having a lot of small files and doing a lot of small IOPS. So IOPS here refers to input-output operations per second. So high IOPS workflows are really bad on a system such as Lustre. And in fact, if you run a code that does a lot of small read and writes, we'll probably notice that and we'll contact you and ask you not to do that, to modify your workflow. So what can you do about this? What can you do about a large number of files on a Lustre-like file system? Well, if you already have a lot of small files on the disk, then of course you can reduce their number by simply packing these files into archives. And of course, if you're not actively accessing these files, they're just sitting there statically, this will still help you with your quota because you typically have a quota of something like 500,000 or maybe 1 million files for the entire file system. So use standard archival tools such as tar, dar. So I'm personally a very big fan of dar, which is similar to tar, but whereas tar stands for tape archive, it was developed about 40 years ago, actually more than 40 years ago in the late 70s. DAR is a similar tool, but it's much more scalable because it includes a file index inside each archive, and it's just much more performing, better performing than TIE itself. But anyway, this is going to be so packing files into archives is going to be only a partial solution, because if you are running code that outputs a lot of files, then the problem is still there, right? So ideally, of course, we would love if you modify your code to streamline output, so you reduce the number of files. Instead of writing into a lot of small files, you write into a few large files. But of course, we realize that sometimes it's just not possible. Maybe you're running community code, or maybe you're running code that you just don't have any control over. And so what can you do if you don't have control over the code's output? Well, one possible solution that we advertise in our workshops is to use temporary storage. So a lot of our clusters, actually most of our clusters, have some local drives mounted on the nodes. These drives, when you start a job, you will have inside the job, you will have the slom underscore TMP directory variable that will point to this temporary, so local attached storage. This is going to be much faster than for small files than a network or a distributed file system. So the problem here, of course, is that you have to copy these files out at the end, because if you're writing a lot of files into, well, because this directory is going to exist only for the duration of your job, right? Once the job finishes, the directory is going to be deleted. So don't make a mistake of writing a lot of files and then not copying them out of this local drive. So another possible solution is to use an SQL database. And this solution works for some codes, but for some workflows, but not for everybody, simply because with SQL, you cannot really, write generic large files, simulation output files into a database. But it's really great, for small brackets, small files. And we actually have in a month and a half, we have a webinar on using SQL databases for precisely this purpose on our clusters. But today we're going to talk about container overlay. So there are a few other solutions that I'm not going to talk about today. Today we'll be focusing on using container overlays. So what is an overlay? Or an overlay image is a file that appears as a single regular file to the host file system. So when you log into the cluster and you do, ls -l in this file, you'll see a single file. Probably is going to be a large file, several hundred megabytes or several gigabytes, but you can mount this file as a Linux, so typically an X3, so Linux-based file system inside the container, right? So inside the container, you will have access to multiple files, whereas outside of the container, on the host file system, you will see a single file. And so this is really great if you want to write a lot of files, and I'm going to show you today several ways of how you can actually output your results, a lot of small files into these containers. So I've realized that probably not everybody today is very familiar with Singularity or Aptina containers. So just a couple of words on this. By the way, this is called Singularity/Aptina. So the new name is Aptina. So Singularity was a project that started about 8 years ago, and it was called Singularity, but a bit more than a year ago, it actually split into two branches. So there is a commercial branch that is now called Singularity, and there is an open source branch that is called Aptina. So for recent versions of Singularity, we use Aptina on our clusters, but still for older versions, you will find the modules that are called Singularity, Singularity, and then some version number, right? So when I talk about Singularity and Aptina, I'm talking about the open source, the recent open source Aptina version. So what containers do, they essentially create a custom secure virtual Linux environment on a Linux system, on a host Linux system. And this environment can be different from the host operating system. So for example, most of our clusters in the lines are running some version of CentOS. And let's say you want to run a code that is available as a binary package compiled, let's say, for Ubuntu operating system. So you can simply start an Ubuntu container and then install that package inside the Ubuntu container, and then the binary precompiled code will run just fine inside the Ubuntu container, whereas you won't be able to run it natively on the host operating system. So these containers are very lightweight compared to virtual machine. There's almost no overhead, and they're really great for creating these sort of custom software environments where you can create a container with your favorite tool and dependencies, and then you can run it on different clusters, in different HPC centers, etc. So it's really great, and it's been designed for portability. So here is a diagram that I created for our summer school containers course. But the thing that I want to show here is that containers, so typically when you work with Singularity or Aptina containers, they typically exist as a single .c file on your host file system, right? So you can take this C file and run it in a variety of ways. So you can start a shell, you can say Aptina shell, followed by the name of this .cif image. Interactive shell inside the container, or you can run a specific command. So Aptina exec will run a specific command Aptina run will run a predefined default script inside the Aptina. So there are multiple ways of using these Aptinas. Where do you get the C file? Well, perhaps you just copied it from, from a, let's say, it was provided by the HPC, your HPC center, or perhaps you took an online, online existing container, let's say Docker container or a Singularity container somewhere in the cloud, and then use the Aptina pool container name command to pull it, to save it as a local file, and then you'll be able to run this as a container on our system. If you want to modify an existing container, there are several ways of doing this. So you can convert an existing container into a sandbox, right? And then you can modify it, you can install packages. So sandbox is going to be not a single file, but it's actually a directory on the host file system. Then you can install things into it, and then you can convert it back into a single container file. You can also create a container from scratch by using a so-called definition file. And I'm going to show actually examples of all these workflows today in lots and lots of demos. So the blue arrows here show workflows for which you typically don't need to have root, right? So you can be a regular user, whereas the gray arrows show workflows where you need to be root. So there are some workarounds, and you don't have to be root to do everything. So for example, in recent version of Aptina 1.1, you can actually do quite a lot of things by using --fake root command. So you'll be able to actually build containers and modify existing containers without being root on the whole file system. But anyway, so let's just jump to some demos. So here's a slide. All commands I'm going to show you, they are in the slides. But what I'm actually going to do is I'm going to copy them from a clipboard in a separate text file that I have on the other screen. So what I'm going to show here is, let's just start a container. I'm going to log into a cluster. So this is a training cluster, that we use for training. And the reason I'm using it today is because it has exactly the same software environment as the clusters in the Alliance, so in formerly Compute Canada. So exactly the same software environment. But here, when I start a job, so I'll be starting lots and lots of jobs today. When I start a job, it will start immediately. So I wouldn't have to wait, in the queue, because right now I'm the only user on this system. But everything I'm going to show you today applies in exactly the same way to a real production system like Cedo, Graham, or Niagara, etc. So the first thing I'm going to do is I'm going to load the Aptina module. So I'm going to use a fairly recent Aptina 1.1.3. And then I'm going to, so I already pulled the Ubuntu container from an online Docker image. So here's a starting Docker image in Docker Hub, so online Docker repository. And I already have the ubuntu.zip file. It's actually a really small file, right? And in order to, so let me select shell. So I'm going to say Aptina shell, followed by the Ubuntu container name, right? So now I'm inside the Aptina. I can actually run commands inside the Aptina. So inside the Aptina, I'm the same user as outside the container. And this is actually the general rule with Aptina/Singularity, is that you are exactly the same user inside the container as outside the container. So if you have root privileges outside the container, you will have root privileges inside the container, and vice versa. So right now, I'm just regular user. I don't have any super user privileges. And just to show you the operating system inside the container, so I can actually do cat on these /ads/os release file, and you see that inside the container, I'm running Ubuntu 22.04. All right, so I'm going to exit the container. I'm back to the host system. And the next thing I'm going to do is I will actually create a small overlay file. So I will run this command. I'll just paste it instead of, so I don't have to type. I'll just paste it from my clipboard. So I run Aptina overlay create size 512 megabytes, so half a gigabyte. Overlay file called small.emg. So today, throughout the whole presentation, .emg will refer to overlay images, whereas .cif will refer to container images. All right, so here it gave me a warning message that you're not using --fake root, and actually I don't need --fake root because I'm not going to be writing any root files into this container. It's just going to be all user level files. All right, so here it created a small image, which is half a gigabyte, so 512 megabytes in size. And then I can mount this image inside the container. So to mount it inside the container, I'll just run the previous command, but I will add --overlay followed by the name of the overlay image, right? So this overlay image appears as a single file to the host, but inside I actually can have as many files as I want, right? Well, as many files as the disk space allows me. So I initialize a half gigabyte container. So if I do the df minus key each to look at all file systems, or actually all file systems available to me inside the container, you see that one of them is a writable file system called Fuse Overlays, and this is actually the file system provided by the container. So there's some overhead that comes, with the container overlay software. So the writable space is slightly smaller than 512 megabytes. This is what it is. So you have to account for, a little bit of overhead when it comes to overlay images. But here's the writable image, and I can actually write into it. So let me show you how we can do this. So I'm going to create a directory, root level directory /data. And then I'm going to go cd into that directory. And now if I do pwd, you'll see that I'm in that root level directory. So here I actually created a directory inside the overlay image. So if I type df minus key each dot, it shows me the current file system. So right now I'm on Fuse Overlay. So the general rule is that inside a container, everything is read-only. You cannot, in general, when you mount a container, you cannot modify files inside the container. But if you mount a writable overlay, you can modify, write, read, delete files inside the writable overlay. So when I create inside the container, when I mount a writable overlay, and I create a top-level directory, this top-level directory will go always inside the overlay file system, right? Because I don't have write access anywhere else inside the container. Okay, so by default, whenever you create, when you have an overlay mounted, and when you create a new top-level directory, for example, I can create a new top-level directory, let's say results, that will go into the overlay image as well. Okay, and then inside here, I can actually create, as many files as I want. Let's say touch. Let's create, I don't know, a dozen files. 10 files. So here are my files. They are inside the /results directory. Then I exit the container, and then I simply remount the container, and then I do ls minus ls, so the results is in the results. And here you see that here are my files. All these files appear as individual files inside the inside the container, but to the host operating system, they're actually a single file. All right. So let's try to write something a little bit more significant. So let's just, so I initialize a half gigabyte container. Let's just write a few hundred megabytes of data into it. And the way I do this, I'm organized this loop where num goes from 0 to 19. So there are 20 files going to be created. And each file is going to be a random file, a random data. That is going to scale from 1 to 33 megabytes. So then the result is basically this will take roughly 350 megabytes of data. So let me just copy this code. And of course, I want to run this code inside the overlay directory. So let's do it inside results. So here we go. And then I actually run this. So it will take a few seconds to run all of these loops. So it just runs these, random files inside the overlay. And there will be 20 of them, so almost done. Okay, all done. So as you can see now, if I type du minus k each, I can see usage on this file system. So right now, 378 megabytes I use actually df minus k each for the entire file system. So you see that I use most of the file system is now taken by this file. So in fact, I can exit and I can remount my overlay on the Ubuntu container, and then I'll simply do ls results, and you see that all these files are right there. All right. So you can also create an overlay image with a directory inside of it with a single command. So when you create the overlay with obtain overlay create, you can simply pass the -- create directory and then the directory name flag. and that will create a directory inside the overlay, right? So that simply saves you from typing make directory command inside the container. You can also mount the overlay image in the read-only mode. So let me show you. Let's mount the same overlay image in the read-only mode. And then let's go to results. So here are files. And then let's try to write, I don't know, b.txt file. And you will see that now I cannot do it because this is a read-only file system, right? So why do you want to mount containers as read-only? I'll talk about it in much more detail later on in this presentation. So you can also resize a container image. You can size it up and down, which is really great if you're, let's say, running out of space or you want to get rid of, unused disk space. And the command for this is resize to FS, so the regular Linux, partitioning command. And then you can size down. You can actually size it down. So if you, let's say, if your overlay image is empty, you can actually size it down to, so I tried it, the minimum size is 60 something megabytes, and then obviously you can size it, to any larger size you need or you want. So Obtainer also supports sparse images. And the idea of sparse images actually not unique to Obtainers. It's something that has been available in the Linux kernel for quite a few years. And the idea is that if you have a file where a lot of blocks are not stored, you can actually store it as a sparse file. So the idea of a sparse file is that a lot of stuff inside of it is actually not going to be using this space, right? So here I, for example, create a sparse overlay image, right? So you see that there's sparse flag, and then if I do ls -l, it will actually appear as declared size, 512 megabytes. But if I do a du -h sparse image, it'll be much smaller. It'll actually show its actual size, which is much smaller than the declared size. So we don't really advertise sparse files much in our documentation because it's actually really dangerous to use them. So the problem is that not all Linux or Unix utilities support sparse files. So for example, when you take a sparse, almost empty file and you compress it with gzip, it works. It will compress to a tiny file because it's mostly empty. But then when you use gzip, it will turn out that this file will actually be restored into a non-sparse file, right? So it will take much more actual space on the disk than the original file. So commands like secure copy, secure FTP also don't play nice with sparse files, right? So be careful. The point here is that if you think that sparse files is a brilliant idea and it can give you a lot of flexibility, provide a lot of flexibility, and at the same time save disk space. Be careful, because if you're not, if you are using the wrong tool with sparse files, it can actually, balloon in size to much bigger physical files. But the point here is that if you know what you're doing, then container overlays support sparse images. So containers are really great for creating any software environment. Well, container overlays for creating any software environments where you have a lot of files. And here's an example of installing conda inside an overlay image. So you probably know, or maybe you've heard it from us, or you've seen it in our documentation, that installing conda or anaconda packages, distributions in our clusters is a really bad idea. So in fact, we actually have a web page that tells you exactly why it is a bad idea, right? So there are several reasons. One of them is because underneath it uses a lot of files that will contribute to your quota and will make things more difficult. But of course, you can actually install a conda distribution inside an Obtainer image. And the beauty of this is that you actually need root permission. If you use Obtainers, you don't need root permissions to actually install conda in there. So you can do it in several different ways. Here's how I would do this. So I will actually bootstrap a new Ubuntu container from online from Docker Hub, and then I will create a sparse image. So let's say if you don't really want to install any big Python packages, just want to install the basic conda installation with Python, then you probably need around 550 megabytes. So here I initialize a sparse image, 550 megabytes in size. Then on the host file system, I download the conda installation tool, and it's just a bash script. But the reason I download it on the host image is because if you so in the default Ubuntu container, you don't have a wget tool. So if you want to install it, then you will need to have root permissions, right, in general. So I download this file to the host file system, and then I start the container loading my new sparse image as an overlay image. Then I go into the sparse image, and then I create a conda directory in there, and then I run the sparse image. I run the installation script from the host file system, and this image is sitting in my Scratch folder. But because I mounted the Scratch folder inside the container, this file is available to me inside the container, right? So I agree to the license. I specify, so this is very important. If you want to install it inside the overlay image, you have to specify not one of the host file system directories, but you have to specify the directory inside the overlay image, right? And then you probably want to say no to initialize miniconda 3, otherwise it will try to overwrite your host file system .bashac file, and then basically it'll take a couple of minutes, and then it will install almost 18,000 files inside the overlay image, right? And then you can simply mount, anytime in the future, you can again mount this container. So the container you didn't write anything into, right? It's just a stock container, and you can actually use instead of this image, you can use some other Ubuntu compatible container image, and then you mount the overlay image into it, and then you simply source the initialization script, and then you run Python as normal. So if you want to install any packages, here's an example of doing it with NumPy package. So NumPy package actually takes quite a bit of it. Takes about 1 gigabyte of extra space compared to the previous installation. So usually, I mean, you probably want to account for this when you create the this overlay image in the first place. So here I'm creating a new overlay image called conda.amg, but I'm asking for 2 gigabytes of space because I know that NumPy will take a lot of space and has a lot of dependencies. And then I simply install things as usual, as described in the previous slide. But then I also I exit the container, and then I mount the container with -c flag. So -c flag will prevent mounting of all local host directory, all the classes directories inside the container, except for the one that I specify here. So Scratch will still be accessible. But the reason I'm doing -c because otherwise, when you try to do conda install NumPy inside the overlay, you'll actually get an error message, because by default the conda installation scripts for Python packages will try to write into system directories, so into adds directory on the host file system, and that will produce an error because you don't have write permissions to those directories on the cluster, right? But if you hide those system directories, the installation script is sufficiently smart that it will just install everything inside the container, and then you will simply be able to start Python inside the container and run NumPy right inside Python. Okay, so let me now, if there are no questions, let me actually now go to the more interesting topic of running MPI codes inside a container. So there are fundamentally 3 different ways to run parallel MPI codes in a container. One of them would be to rely on MPI inside the container. So that means that on the host, on the cluster, you will see something like uptainer, and then possibly some flags to the uptainer, and then you will eventually call MPI run, but this MPI run will run inside the uptainer process, right? So you're starting a single uptainer process on the node, and then inside the uptainer process, you are using MPI run, which is entirely inside the uptainer. So this works well on the cluster, but the problem here is that this setup will be limited to running your code, MPI code, on a single node, because you're relying on a single uptainer process that is running on some node, and that process cannot simply spawn any Unix processes on other nodes on the cluster. So this is really limited, but the plus of this method is that you don't need to adapt containers MPI to the host. Just install basic SSH package into the container, and this will work. I actually have an example for you in a couple of slides. You can also run an MPI code in a container in a hybrid mode, where you rely on MPI run, so the routine to start the MPI code from the host, right? So MPI run comes from the host, and then with MPI run, you actually start, some number of obtainer images, obtainer processes, so one obtainer process per each MPI run in your code, right? So this MPI run comes from the host, but then the MPI code was actually compiled inside the obtainer. So that means that inside the obtainer, you are going to be relying on the runtime MPI libraries. And so that means that these libraries should actually be compatible with the MPI and Slurm setup on the host. But it's actually, I'm going to show you how to do that. It's actually not that difficult, right? And so this hybrid mode is the one that I'm going to mostly demo you today because it's just a lot more flexible. There's also what is called a bind mode, and this simply relies on mounting all the system directories with MPI, so the host MPI inside the container, and using just that, both to compile the code and in runtime, but I'm not going to show you an example of that today. So today I'm going to show you demos with OpenFOAM, which is a very popular package for computational fluid dynamics. And the reason I'm showing it today is because OpenFOAM is really notorious in that it creates a lot of output files. So a typical, OpenFOAM simulation can easily create millions of files that will contribute, to the many file problem on the last file system. So there are two ways of running OpenFOAM inside a container. One of them is you can build a basic Ubuntu container, and then you can install OpenFOAM. You will need to be root for that. You will install OpenFOAM, one of the recent OpenFOAM packages as a binary package inside the container. And it's really easy to do. So I actually have all instructions linked from this page right in slide 13. Slide 13. So here are all instructions. I won't go through this demo because it's not the best way to run OpenFOAM in my way, because this run is going to be limited to a single computational node on the cluster. So in general, this setup will not play nicely with the host MPI. So that's why I'm not going to spend any more time on this. What I really suggest is to run OpenMPI inside the container in a hybrid mode, where you use MPI both on the host and on the inside the obtainer. And so there are actually the steps that are involved. So I'm going to go through the steps 1 to 7. And this is going to be just the rest of my presentation that I hope to finish in the next 20 or 25 minutes. So the first step is to build an MPI container, because we're going to be running MPI code relying on MPI both inside and outside the container. So the MPI MPI installation inside the container has to be compatible with MPI on the host and with Slurm on the host, right? So they can talk to each other. And this is actually not as difficult as it sounds. So basically on the host, what do you need to do? So here I'm on the host. You will just scroll down to my commands. You will need to check what kind of MPI you need to. Oops. Beautiful. Yeah, it's frozen now, so I need to open a new window, close this window. And then open a new window, because the SFU network times out after a few minutes of inactivity. Okay, so I'm actually, so that I'm running into the same problem again, let me connect again to my training cluster, and then I'll actually do things inside TMX. So I'm gonna go into into my directory with all these containers, and then I'm gonna type srun -MPI list. And so what it will do, it will show you various PMI mechanisms that are supported by the host Slurm and the host MPI run. And you see that one of them is PMI. PMI2. So that means, so PMI stands for Process Management Installation, I guess. I can't remember, always forget that. But basically, it's a way to spawn processes with MPI run, right? So MPI run itself doesn't spawn processes. It relies on PMI software, PMI interface to launch processes that later on will talk each other in the same job. And so PMI2 is the way this is done on the host. Actually, this is the same mechanism that is available, that is used on CEDA, Graham classes and so on. So I'm pretty much sure that everything that I'm showing you today on the training cluster is going to be can be applied exactly the same without any modification to our production clusters. So anyway, so we need to support MPI2. So that means that when we create an MPI container, we have to install the compatible Fabric and PMI packages, the Slurm client, and there are a few other requirements as well. So this takes something like 10-20 minutes to run all of this, and actually link the exact recipe for creating the MPI container that is compatible with our clusters right here. So you will start with the definition file. So here's a definition file, right? And then basically it will say sudo, so you will need to have root permission, sudo obtainer build, let's call this container mpi.cif, in this image mpi.cif, and then we are taking all these commands from our definition file. So this takes around 10 or 20 minutes, and then at the end, what you will have is the mpi.cif container. So here's my MPI.cif container, MPI.cif container, oops, sorry, MPI.cif container. And as you can see, it's just under 300 megabytes in size. So it has the MPI distribution and all the dependencies that will talk nicely to the host Slurm and to the host MPI. Okay, and then let's just test a very simple code inside the container. So what I'm going to do is I will take a code, distributed pi.c, that I use in training. So it's a basic MPI code, distributed pi.c, and oops, more on this code. And then it basically, runs some MPI commands. So let me compile this code. So I'm going to say to compile the code, I'm going to issue this command, obtain exec -b scratch MPI.cif, and then MPI-cc. So here I am running just a single instance of obtainer. So there's no parallel execution, it's just compilation. And then inside that obtainer, I'm running MPI-cc command to compile my code, right? So I do this, and as you can see, now I have the new file that I can run only inside, so distributed pi, right here, that I can only run inside the container. So actually outside the container, if I try to run it, you see that there are library problems, and that's simply because things were compiled for use inside the container. And then I'm going to run it, right? So to run it, I will simply start the, actually, let me see. I will start the shell. Actually, I will do the exec command. So I'm going to say obtainer exec, and then I'm going to mount my Scratch file system, so MPI.cif container that I just created, and then inside the container, I'm doing MPI run. So here I'm relying on MPI run inside the container, right? Okay, and let's see, it worked, it didn't work. And it didn't work. Let's see what I did wrong. So let me do it again. Oh. Module. I probably didn't load the right obtainer module. Oops, let me see. So I loaded the right obtainer module. Maybe I forgot to do it before. I compile the code. And actually, let me, the one thing that I should probably have done is start a parallel job. So here I'm starting a job asking for three cores on one node. And then I'm simply running the code in parallel. Yes, beautiful. Yeah. The problem was that before I forgot to load the obtainer module, and B, I forgot to start the parallel job, right? So here I'm inside the parallel job, interactive job, and then I started with Solog, and then inside the job, I can actually run the code. So as you can see, the code runs just fine, and it started 3 MPI processes, but in fact, in the setup, there is a single obtainer process. So I'm relying on MPI run right inside the container. So let's try to do something similar with OpenFOAM. So with OpenFOAM, I would need to install OpenFOAM into my MPI.cif container. I won't do it now because I shall take a few hours. But the way I would do this, I will take my existing MPI.cif container that I just used, and I will convert it into a sandbox, right? So sandbox is basically a directory on the host file system where I can modify files. And as you can see, in order to do that, normally I have to be root, right? So I cannot do this easily on the cluster file system unless you're using the -- fake root flag. And then, so normally I suggest to run these 2 commands somewhere on, either on your own computer where you have root access, or perhaps in a virtual machine. So in a virtual machine, this will work just fine. And then, so after I create the sandbox environment, I mount this sandbox environment in a writable mode, right? So that means I'll actually modify files inside the sandbox environment. And then I simply go into the installation into the /opt /OpenFOAM directory, and there I download OpenFOAM. I'm going to show you demos with OpenFOAM 1912 because the most recent major version actually has some bugs that prevent me from using it with overlay images. And I'm not sure what those bugs, but they're really, really strange, I would say. Anyway, so basically I go into this directory and then I install a couple of packages and then I source the initialization file, and then I compile OpenFOAM right inside this container. And when I use 8 cores, it actually took an hour and a half, right? So this whole setup takes a while. And then I exit the container, and then I go back into, I convert back the sandbox into a new image that I call openform1912.cif, and then I copy it out to the cluster where I'm going to run it. So let me just show how I can run it easily inside this whole setup, how I can run it using the clusters API run, right? So let me actually create, so I'm going to be writing results into an overlay directory. So here I'm creating a directory called, into overlay image. I'm creating an overlay image called output.image. It's 100 megabytes in size. And then I'm going to load this image into, actually, I probably don't want to do this inside the job. I exit the job, and then I'm going to load this output overlay, output.img overlay image into my OpenForm container. And then the next thing I need to do is source the OpenForm setup, so I actually have access to all the proper executables. Then I'm going to go into results directory. So the results directory exists there because I just created a minute ago inside the overlay, right? So I go inside the results directory, and then I'm going to copy some test code. I'm going to CD there, and then there are a couple of things that I need to modify. So I need to rename one of the files, and then I'm also going to add it. So I'm doing all of this inside. I'm setting up my OpenForm simulation inside the container. I'm going to edit this guy. And so this file actually tells me how my parallel simulation is going to be decomposed. So I'm going to run it on 3 cores. And then I'm going to use a 3 by 1 by 1 decomposition, right? So it's going to be decomposed in the X direction. And another thing that I want to modify is, so it's going to run up to n times 500. But then I want to have more outputs just to show you the problem with many files. So I'm going to do an output, entire simulation output every 10 time steps. Okay, so I'm going to exit this, and then I'm going to rename another file because it needs to be removed. Renamed, then I create the mesh with block mesh. So it creates the mesh, and then I decompose my my simulation, the initial conditions and the mesh, right? So the end result of this is that now, because I'm creating a simulation for 3, so remember I specified three blocks, right? It will be decomposed into 3 parts. Now I have 3 directories: processor 0, processor 1, and processor 2 in the current working directory, and this contains the initial conditions and the decomposed mesh, right? And then the results, when I run the simulation, the results will actually go into these directories: processor 0, processor 1, and then processor 2. So I just exited the container. I need to set up a couple of variables on my host so that inside the container, you'll be able to find OpenForm installation. And then I'm going to run the simulation. So I'm going to start a parallel job on the host, right? So Salog all on a single node. The reason I'm doing this on a single node is because I'm relying on MPI run inside the container. So a single obtainer process, MPI run inside that obtainer process. And then I'll be running on 3 cores. And then I'm going to run the actual simulation. So the way I run the simulation is by using this command. And here the simulation runs. It'll run to time 500. So now it's time 100. So it'll take maybe 10 more seconds, 15 more seconds. And you see that all results will go into the processor directories that are mounted, that exist there inside the overlay image. Okay, oops. So I think almost done. A couple more seconds. Okay.
So
great.
Alex, you have a question in the chat.
Sure. A question: is there an option for the container overlay image size to grow as files are written to it? Yes. So if you specify a sparse image, that's exactly what it will do. But you need to use the sparse image for that. So basically, initialize a very large sparse image that is that is slightly bigger than the end size of your output results, right? And then the actual size of the sparse image will grow as the simulation grows. The answer is yes. All right, but you have to use sparse images for this. Okay, so inside the container, let's analyze the results. So we just ran the simulation, and the way I analyze the results is I will have to, so all results are actually stored. So here I just exited the job, and all results are actually stored inside this output image directory, right, which is just a single file in the host directory. So I actually have to mount it to a container, And you can do this on the login node, but of course, probably if you want to do some heavy processing, you want to mount this on the not on the login node, but inside a job on a compute node. So here I started a single task interactive job, and then I'm going to mount it inside the container. So my OpenFOAM container, here's my output, right? And then I simply go to CD results. So this directory is inside my overlay image, motorbike, and now I have all these processor directories that I filled with the results, right? And in fact, if I count the number of files, you will see there are 1,542 decomposed files. So if you want to reconstruct this, so decomposed and reconstructed files, this is an OpenFOAM speak, but essentially what it means is that by default, OpenFOAM will let each processor write into its own directory, right? So here are outputs of individual processes, individual MPI runs. And then if you want to have a single non-decomposed result, then you have to run the reconstruct command. So this command, when you run it, so then at the end, you will have almost 2,500 files. Now you have reconstructed files, you can get rid of the decomposed files. But even if you do that, you still have about 900 files that include the results and the setup. So it's a lot of files, right? It's not 1,000 files, 900 files is not such a large number. But if you actually scale it up to real production runs, so a typical OpenFOAM production run will have maybe 1,000, maybe a couple of thousand time steps, 128 cores, 10 files, so 10 variables per core per step, and that will easily give you several million files, per simulation run, which is a lot. So now, of course, the important question is, how do you scale to multiple nodes? And the setup that I showed does not scale to multiple nodes, right? Because in the simulation, you're actually relying on a single obtainer process, and inside that single obtainer process, you are running MPI run, right? So here you're running MPI run. But this MPI run cannot scale to other nodes because it really relies on, on the host single obtainer process. So to scale to multiple nodes, you have to use the host MPI run. So you have to do something like MPI run, right, inside the job. And then for each MPI rank, you will start an obtainer process. But then there's a big complication. So now you have multiple obtainer processes and you have a single image. So the problem is that with obtainer, you cannot mount the same overlay image in multiple containers at the same time. That's the fundamental limitation, right? So what do? Well, fortunately, it turns out that you can actually trick OpenFOAM into thinking that it's writing into a uniform file system, whereas individual processor directories will be links to the content inside overlay images mounted on individual MPI ranks, right? So if this doesn't make sense, I will show you the demo right now. And this idea actually picked up from the Pawsey Supercomputing Center in Western Australia. I haven't seen it anywhere else, so I'm not sure how widespread the solution is. But as far as I can tell, it's really a great idea and it works really well. And the performance is really, really good. So the first step is that you will have to, actually, let me skip this slide because I'm already close to the top of the hour. I don't have a lot of time. So let me show how I can actually set it up in such a way that you have multiple results from individual processes going into different overlay images. So the way you do this is you will have to, let me actually exit the container, and then I will set up a variable. So this variable appears in the slides as well. And the reason I need to set it up, otherwise I will get some, some warnings that actually, as far as I can tell, they are not particularly important. And then let me delete all previous OpenFOAM results. I probably didn't have anything there, but let me actually clear the directory so that I start from a fresh setup. And then let me let me start a single obtainer image. So right now I'm not running the code, I'm just preparing the simulation. So I'll do this on, actually let me exit, I forgot we're still inside the compute node. So now I'm back to the login node and I'll be preparing simulation, so nothing particularly CPU intensive. So here I started a OpenFOAM container, just a single instance, no MPI run, right? And then I'll be preparing simulations inside this container. So let me load the setup, right? So then I'm gonna create a directory and cd into this directory. But notice that this directory, actually now my simulation directory exists not inside the container, but on the host file system. So this is very important. And then I simply copy my my test run into there and I cd into this directory. So now this is sitting on I'm inside the container, right? Inside the container, but this is on the host file system, right? So as you can see, this is my Scratch folder, right? So now let me rename this file that is necessary to run this code. And then let me actually quickly do the same setup I've done before. So I'm gonna do run on three MPI ranks. So I'm gonna decompose it into 3 partitions, and the decomposition XYZ is gonna be 3, 1, 1. And then again, I wanna have a lot of output. So I'm gonna have output every 10 time steps, right? Now, let me rename another file, not sure why those names are there. And then what I'm gonna do next is I'm gonna create the mesh, and then I'm gonna decompose this mesh. So now we see that now I have these individual processor directories with initial condition and the mesh for the simulation decomposed into 3 pieces. I'm gonna exit the container, and here where the magic comes in. So now what I'm gonna do is I'm gonna archive, so basically move out of the way these processor directories. So here I'm going to go to my simulation directory outside of the container on the host. So there are no containers. Oops. Let's see, CD, I probably renamed it. So CD, Scratch, OpenFOAM. Okay, run motorbike. Oh, I see. Run motorbike. So here I take all my processor directories and I move them into a temporary directory that I'll call back. I mean, it's just some temporary directory, right? But the point is that they're no longer here in the simulation directory. And then I'm going to create in an overlay image. So because the minimum size of an overlay image is around 65 megabytes, so I'll just create a 100 megabyte overlay image. It's still fairly small, right? So I'm going to call it results 0. And it's going to be a 100 megabyte overlay image. And then I'm going to copy it into 2 other overlay images. So I'm not going to create those from scratch. I simply run a loop and copy results 0 into results 1, and then copy results 0 into results 2, right? So now I have exactly identical copies of a 100 megabyte overlay image. And then what I'm going to do is I will mount them one by one. So I mount the 0th one, the first one, and the second one. And I will copy the content of my archive processor directory into these overlay images. So basically, this is what I'm going to do. I'm going to cycle through these overlay images. There are 3 images because I'm going to run my simulation on 3 partitions. And then I'm going to move the content of my partition mesh and partitioned initial conditions from my archive, .back archive, inside the container, inside in here. And I probably should modify my commands because I guess I have, actually, let me try to see if it works. So I think I have a typo in my notes. Let's see. So, okay, that didn't work because I need to have run motorbike. Just an improperly mounted directory. Okay, results run. Let's see why. Sorry about that. Yeah, it's just I renamed the directories and I didn't do it everywhere in my notes. So there's some inconsistency. So let me try this. No. Okay, well, yeah, unfortunately, I'm running out of time, so I only have 5 minutes left. So believe me, this works. So I tested over and over again. So, but there is something wrong with the directory names, and I won't be able to fix it in a few seconds. So yeah, I think you had to go back to Scratch before running that, where you have openfoam.c files. Okay. Yeah. Anyway, sorry about that. Yeah, because I'm running out of time, so I'll just go to the slides and we'll talk about it. So basically, the idea is that you will copy the initial conditions and the partition mesh inside the corresponding overlay directories, right? And you can actually check the results, right? For example, if you mount, oh, actually, yeah, one more step. You create symbolic links from inside the run directory, from inside the simulation directory on the host file system, right? So this is on the host file system. And then there, you're actually creating the symbolic links that point to inside the overlays, the individual overlays per MPI rank, right? And the way you can check the content of these directories, you can mount them one by one, right? So for example, here, I mount result 0 image, right? In serial. And then when I do inside the simulation directory, inside the container, so inside this directory, when I do ls processor, it will only show files inside processor 0 directory, because the other two links won't work, because results 1 and results 2 are not mounted, right? But of course, inside the simulation, you will mount all three of them. So the way you run the simulation is, once again, you set up the necessary environment variables on the host, and these are necessary so that inside the obtainer, the system can actually find, all the OpenFOAM files, and then you start your parallel job. So in this case, I'm starting the job on 3 cores, but this time I'm not limiting to a single node, right? So it's going to run on 3 cores anywhere on the cluster, and then I run the following command. So I run echo, and then I'm pasting these very large line into srun dash n number of tasks bash. So basically, there is a bash process running on each of my MPI processes and which of my MPI ranks, and then that bash process will run this command inside the single quotes, right? So basically, on each MPI rank, I start a container into which I mount the properly named overlay image, right? So on rank 0, it will mount results 0.image. On rank 1, it mount results 1.image. On rank 2, it will mount results 2.image, right? So each inside the job, each MPI rank will be able to run into, following those symbolic links, run into the corresponding directory inside the corresponding obtainer, right? And then once the run finishes, you can actually check all of them while still inside the simulation directory. So here I'm simply mounting all of them, all of these overlays, so results 0, results 1, and results 2 inside this obtainer, right? I'm mounting them in parallel, so each one of them is going to be mounted on each processor, and then inside that processor, I do ls processor, and then the corresponding MPI rank, right? So that means that each processor will see its own part of the simulation results, right? So now, if you want to, this is the run, right? And this run actually scales beautiful. So I tested it on multiple nodes, works really well, and the scaling works really well as well. So you're not, if you run on n nodes, it will be, sufficiently faster than running it on a single node. So now, if you want to post-process these results, you have two options. You can reconstruct them, or you can actually analyze and visualize these results in decomposed mode. So after your simulation, all results will be decomposed, right? So we'll be sitting inside those individual processor directories. And then what you can do is, unfortunately, you cannot mount multiple writable overlay images per single container. But what you can do, you can mount multiple overlay images as read-only, right? And then a single writable image. So what I'm doing here is I'm starting a serial job, and in this serial job, I'm mounting all the results, right? So when you do this actually, let me just type this. This actually expands into, results 0, image in read-only mode, results 1 read-only mode, results 2 read-only mode, right? So you mount all the results in read-only mode. And then you have a new container that I call reconstructed DMG that is actually slightly larger than those, right? Well, 3 times the size, because I have 3 100 megabyte result overlay images, right? And then I'm combining all of them into a single overlay that's now 300 megabytes in size. And then I simply CD into the, I go into the simulation directory, and I simply move everything from the previous simulation directory on the host, including the links, inside into a directory inside the reconstructed overlay, right? And this move actually doesn't move a lot of data because the results will not be moving, right? So you're not actually moving the results, you're just moving the initial setup and the links, which is not a lot. So it will take maybe a couple of seconds. And then you go into the directory to which you moved everything. And then you do the reconstruction there. So the usual reconstruction. And the reconstruction will write into that /analyze directory that exists entirely inside the reconstructed image, right? So the end result is that at no point during the simulation or during post-processing reconstruction, your host operating system is exposed to millions of files, and this is exactly what we wanted. So if you don't want to reconstruct, you want to just analyze and visualize these results, it's also possible in entirely distributed mode. So in this case, let's say we want to use ParaView, right? So you can create a new container into which you install ParaView, a parallel ParaView server. Let's just call this container paraview.cif. And then you will simply start this container in parallel, right, using exactly the same number of cores as in the simulation. And then into this container, you mount the results images in parallel, right? So each one of them is going to be mounted on the corresponding MPI rank. And then, so you start the ParaView server in this way, in parallel, mounting all the results. Then you take note of the listening node's name and the port number. And then you basically connect to this listening ParaView server from your ParaView client on your computer, right? And the way you do this is described in this slide. And then once the connection is established, you go and create an empty keys.foam file inside the simulation keys directory. Make sure that when you load the file, before you hit apply, you specify inside ParaView GUI, you specify case type decompose. So it actually knows that it's loading decomposed files. And then you'll be able to analyze and visualize your simulation without actually, again, ever exposing the cluster's file system to multiple files. All right, so I think I will stop here. I'm slightly out. Yeah, it's 3 minutes past the hour, so out of time. But basically, to summarize, overlays are a really great way to run simulations, and there are multiple ways to to store simulation results. So there are multiple ways of running MPI inside Aptena. I really, really highly recommend to scale beyond a single node. So, but to do that, you have to use hybrid MPI. So both MPI run on the host and then runtime MPI libraries inside the container. And then depending on how your code does a simulation, so you can have one or several scenarios. You would you would do the corresponding setup, and then you'll be able to store your results inside the overlay images. So if you have any questions, feel free to ask them now. My email address is on the title slide. So it's alex.razumov@westgi.ce. So if you ever need help with any of this for your own simulation code, let me know, and I'll be more than happy to help you with the setup. And as far as I know, things work really well. So of course, I can think of some cases where you'll need to be a little bit inventive, but basically, I think that's not so difficult. So everything could be done using something similar to the setup shown with OpenFOAM here. So yeah, I will stop here. Are there any questions inside the chat that I need to answer?